When time almost stops. In the last episode, we discovered that gravity changes the rate at which time passes. A clock on a mountain ticks very slightly faster than a clock in a valley. Satellites above the Earth keep time differently from clocks on the ground. And modern navigation systems only work because engineers take Einstein's theory seriously. But if gravity can change time here on Earth by a tiny amount, what happens when gravity becomes extreme? What happens near an object so dense, so powerful, and so strange that not even light can escape from it? To answer that question, we have to travel towards one of the most mysterious objects in the universe, a black hole. Black holes were not first discovered through telescopes. They emerged from mathematics. Einstein's theory of general relativity showed that matter and energy can curve space and time, and soon after Einstein published his theory, scientists realized that if enough mass were squeezed into a small enough region, the curvature would become so extreme that escape would become impossible. For many years, black holes seemed almost unreal, like strange mathematical monsters hiding inside the equations. Even Einstein was unsure whether nature would actually create such things. Today, the evidence is far stronger. Astronomers have observed stars orbiting an invisible, massive object at the center of our own galaxy. We have detected gravitational waves from colliding black holes. We have even seen the shadow of a black hole surrounded by glowing matter. Black holes are no longer just theoretical ideas, they are part of the real universe. A black hole is not simply a giant hole in space, and it is not a vacuum cleaner sucking up everything around it. If the sun were somehow replaced by a black hole of the same mass, the Earth would not suddenly be pulled in. It would continue orbiting in almost the same way, although of course we would quickly lose the sun's light and heat. What makes a black hole special is not just its mass, but how tightly that mass is compressed. The gravity close to it becomes so intense that space and time are distorted beyond anything we experience in ordinary life. The key boundary around a black hole is called the event horizon. It is often described as the point of no return. Once anything crosses that boundary, it cannot send a signal back out. Not a rocket, not a radio message, not even light. But the event horizon is not a solid surface. There is no wall, no shell, no sudden impact. If the black hole were large enough, an astronaut crossing the event horizon might not notice anything dramatic at that exact moment. Locally, his watch would still tick normally, his heartbeat would feel normal, and his thoughts would continue in the usual way. The strangeness appears when we compare his time with the time measured by someone far away. Imagine two astronauts. Alice remains safely far from the black hole, watching from a distant spacecraft. Bob travels closer and closer towards it. Bob carries a clock, a radio transmitter, and a flashing light so Alice can follow his journey. At first, everything looks normal. Bob waves goodbye, his clock ticks steadily, and his radio messages arrive at regular intervals. But as he descends deeper into the black hole's gravitational field, Alice begins to notice a change. His clock appears to slow down. The flashes from his spacecraft arrive farther apart. His voice over the radio becomes stretched, deeper and slower. The light from his craft becomes redder because it loses energy as it climbs out of the black hole's gravity. This is gravitational redshift. From Alice's point of view, Bob seems to slow more and more as he approaches the event horizon. His clock ticks slower, his movements become sluggish, and his image grows dimmer. In the limit, Alice never actually sees him cross the horizon. She sees him approach it, fade, and become almost frozen near the edge. But this is only Alice's view from far away. Bob's own experience is completely different. He does not feel time slowing. He does not see his watch stop. He does not become frozen. He crosses the event horizon in his own proper time, and if the black hole is large enough, he may pass through without feeling anything special at that instant. This is one of the most important points in the whole episode. Time does not stop for the falling astronaut. Time appears to slow from the point of view of someone watching far away. Bob's clock remains normal to Bob. Alice's clock remains normal to Alice. The disagreement is not caused by a broken clock or an optical trick. It is caused by the shape of space-time itself. Einstein's theory tells us that there is no single universal clock against which both experiences can be judged. Alice and Bob are moving through different regions of spacetime, and their clocks follow different histories. If Bob could hover near the black hole instead of falling in, the difference could become even more dramatic. Imagine a powerful spacecraft holding position just outside the event horizon of a very large black hole. To the crew on board, time would pass normally. They could spend an hour making observations, checking instruments, and looking out at the distorted sky around them. But far away from the black hole, much more time could pass. Depending on how close they were and how massive the black hole was, that single hour could correspond to years, centuries, or even longer elsewhere. In this sense, a black hole could act as a machine for traveling into the future. The astronauts would not travel backwards in time, and they would not break any laws of physics. They would simply take a path through spacetime where less time passed for them than for everyone far away. This idea is dramatic, but it is not fantasy. It is a genuine consequence of general relativity. The film Interstellar used a version of this idea where astronauts visited a planet close to a supermassive black hole and experienced 1 hour while years passed elsewhere. The exact situation in the film was shaped for drama, but the underlying principle is real. Strong gravity can make time pass at very different rates for different observers. There is another important detail. The size of the black hole matters. Near a small black hole, the difference in gravity between your feet and your head could be enormous. Your feet would be pulled much more strongly than your head, stretching your body in a process often called spaghettification. Near a supermassive black hole, however, the event horizon can be so large that the local tidal forces at the horizon are much weaker. In that case, an astronaut might cross the horizon without immediately being torn apart, although escape would still be impossible. The danger would come later, deeper inside, as the pull of gravity became more extreme. Black holes therefore reveal two different kinds of strangeness. The first is what happens to space. Light bends, paths curve, and the event horizon divides the universe into regions that can communicate and regions that cannot. The second is what happens to time. Clocks near the black hole do not agree with clocks far away. Light leaving the region is stretched and reddened. Events near the horizon appear slowed to distant observers. Time becomes something local, dependent on position, gravity, and the path taken through space-time. This matters because it takes us far beyond the old idea of time as a simple flowing river. Newton's time would have passed equally everywhere, whether near Earth, near the sun, or beside a black hole. Einstein's time does not behave like that. It is woven into the fabric of the universe. It can stretch near mass. It can slow in deep gravity. It can differ from one observer to another. A black hole is not merely an object in space. It is a place where the nature of time is pushed almost to its limit. At the very center of a black hole, according to classical general relativity, lies a singularity, a region where density and curvature become infinite and our current equations stop making sense. Many physicists believe this is not the final answer, but a sign that our theories are incomplete. General relativity describes gravity extremely well on large scales, while quantum mechanics describes particles and fields extremely well on small scales. Inside a black hole, both should matter, but we do not yet have a complete theory that joins them together. So black holes are not only extreme objects, they are also signposts showing us where our understanding breaks down. For a series about time, that is deeply important. We began with people watching the sun rise and set. We moved through clocks, calendars, pendulums, quartz crystals, and atomic timekeeping. Then Einstein showed that motion changes time, that there is no universal now, and that gravity changes the rate at which clocks tick. Now, black holes show us something even more powerful. Time can be slowed almost without limit when seen from far away, and yet still continue normally for the person falling in. The universe does not contain one master clock. It contains countless clocks, each following its own path through space-time. So what would happen if you fell into a black hole? From your own point of view, time would continue. You would cross the event horizon, unable to return, moving towards an unknown fate. From the point of view of someone far away, you would appear to slow, fade, and freeze near the edge. Both descriptions belong to the same reality, but they divide time differently. That is the lesson of black holes. They do not just trap light, They reveal that time itself is not what it once seemed. In the next episode, we will step back from black holes and ask an even broader question. If time can slow, stretch, and differ from one observer to another, why does it still seem to have a direction? Why do we remember the past but not the future? Why do eggs break but never unbreak? To answer that, we must leave relativity behind for a moment and enter the world of entropy, where the arrow of time begins to appear.